Today, I'm going to talk about scoring systems. All right, so scoring systems are really tiny little models. They're at the extreme end of interpretable machine learning. It's really hard to believe the power of a little itty bitty model. But before I talk about scoring systems, let me ask you a question. So is it possible that a typographical error could lead to years of extra prison time? Right? That should never happen, right? Typos making decisions? That's crazy, right? Who's making decisions here, a judge or a typo? And would that be fair if that happened? But it happens all the time. And here's an article about exactly this. So this is the case of Glenn Rodriguez, who was in prison since he was a kid. He comes up for parole, and he's denied parole because his COMPAS score is miscalculated. And COMPAS is a black box proprietary model that predicts future crime, and it's used in parole decisions. And yes, a typo made a decision here, not a judge, a typo, and he got years of extra prison time. Now, I want to make a distinction between a black box model and an interpretable model. Okay, so a black box model is a formula that's either too complicated for any human to understand, or it's proprietary, which means we're not actually allowed to understand what's inside of it. An interpretable machine learning model obeys a domain-specific set of constraints so that humans can better understand it. And as we have heard just recently, we need interpretable models for high-stakes decisions or troubleshooting. So things like criminal justice models, credit scoring, healthcare. Anytime it would be bad if the model went wrong, because a lot of times they do go wrong, and they go really wrong. So, okay, what else could go wrong with a black box? So here are a couple of my favorite articles, right? We know that we could send people to prison based on typos, but we also have these other two examples. So over here, this is a case where a black box AI model told everyone that air quality was totally fine during the wildfires and it was safe to go outside when it was not. And then the article on the right is about how he approved deep learning models for healthcare are not performing as well as they should be, and no one knows why. So here, this method, this neural network is supposed to detect intracranial hemorrhages, and it was approved by our FDA. And then they launched it out into the real world and it didn't work, and nobody knows why. And of course, I've given you just a few things that have gone wrong with using black box models, but of course, a tremendous amount more could go wrong, and probably a lot of things do go wrong, and I don't know about them because they were hidden. And now people are starting to use machine learning for all kinds of things, and we, that we really don't want to go wrong, like medical decision making and self-driving cars. And some people love their black boxes. They argue fiercely about why they need them. Anyway, so I want to get back to COMPAS. Do we really need to have black box models? Are they more accurate? And luckily, there was this data set from Florida that got released a few years ago that could tell us exactly how accurate COMPAS is. So we took the COMPAS scores, and they gave us also basic criminal history, demographic information from a few thousand people in Florida. And my lab had developed an algorithm called Corals at the time that the data set was released. And Corals is a really complicated algorithm, but it produces really simple little models. So I want to show you the model that Corals produced on the Florida data set. And the model looks like this. So it says, if the person is 19 to 20 years old and male, predict arrest within 2 years of their COMPAS score calculation. Also, if they're 21 to 22 and they have 2 to 3 prior offenses, predict arrest within 2 years of their COMPAS score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we thought, okay, could that be as accurate as COMPAS? And it was. So what I'm showing you is tenfold cross-validation results. And the different colors are different folds, and you can see that they're pretty much equally performing, okay? And so we thought, okay, now we at least see that COMPAS is not, performing any better or worse than Corals. What if we just threw the whole machine learning arsenal at this problem and see how it did? See if we could get any better performance. And we could not. So this is methods that produce models that are so big that they don't even fit on a PowerPoint slide. So some of these are like, boosted decision trees and support vector machines with radial basis function kernels and random forest. Right? Some of these formulas are so bulky that you couldn't even put them on a slide. And at the other extreme is corals, whose entire model is right here in the corner of the slide. And now, after the COMPAS data was released, there was this huge debate about the algorithmic fairness of COMPAS, but the truth is that we just don't need COMPAS at all. Okay, now you've seen that black box models aren't always more accurate than simple models, but there's some more important general knowledge that I need to provide you. So there's really two broad kinds of problems that we encounter in machine learning and data science. There's problems with tabular data, which looks kind of like this, with real valued and categorical features that are, this is well-structured data. And then there's problems with raw data. So raw data are like images or sound wave or text, where the data doesn't already have a good, the data is not already structured. Okay. And it already doesn't have a useful structure for direct learning, right? So for this kind of data, the only type of method that's working right now for raw data is neural networks. And that doesn't mean that's always going to be the way it is, but right now for that kind of data, that's the technique that's really working. And so while we work on interpretable neural networks, which is obviously a task that a lot of people are thinking about right now, including my lab, we have to realize that there are tremendous opportunities for tabular data, because tabular data is totally different. For tabular data that already has a good representation, with minor preprocessing, all the methods tend to have similar performance. And just like I showed you with the COMPAS data, all the methods tend to perform the same if you're willing to do a little bit of preprocessing. And so what that means is that it allows for the possibility of very, very tiny little models that can perform the same as these big black box models that you might construct. So in other words, what I'm telling you is that the phenomenon that I showed you with the COMPAS data, where everything performed the same, that's kind of happens pretty much all the time with tabular data. All right, so like I said, there's tremendous opportunities with tabular data, but to get really sparse models, but you have to optimize those models well in order to get up to the accuracy of black box models. All right, now, if we think about the history of predictive modeling over the last century, only a small amount of that time did we have data. So most of the predictive models needed to be created by humans in the absence of data. So when we think about, okay, what kind of predictive models do we want to build now that we have data, and we want these models to be interpretable to humans, we need to think about what types of models humans designed in the absence of data. And the most popular form of predictive model, hands down, was scoring systems. A scoring system is a sparse linear model with integer coefficients. So what I have here is an example of a scoring system. This is the CHADS2 score. This is possibly the most widely used predictive model in healthcare. I mean, maybe that and the APGAR score. But essentially, you get points for various things, and those points give you a score. They add up to a score. That translates into a risk of, in this case, getting a stroke within a certain period of time. Okay, this is for patients with atrial fibrillation. Okay, so this model, though, is not, it's not a machine learning model. It's not even a data-driven model. It was designed by a panel of people, and it was validated on data afterward. Now, scoring systems have been used for about 100 years. So I'm going to show a bit of a paper from 1928. This is the Burgess model, the Burgess paper on factors determining success or failure on parole. And Burgess created a scoring system. So he created his own model from 21 factors that he hand selected. And he says, accordingly, 21 factors were selected by which each man was graded in comparison with the average for the 1,000 cases upon the probabilities of making good or failing upon parole. So he's creating a scoring system. It's a 21-point system for making good or failing on parole. And he, depending on the score that the person gets, so how many of these 21 factors they have, that translates into the risk of non-violating of parole. So if you have 16 to 21 factors, your percent is 98.5. Okay, and if you only have 2 to 4 factors, then your percent is 24. And he actually did some interesting categorization of of people in this article. Like, he categorized them in terms of whether they were a ne'er-do-well or a mean citizen or a farm boy or a drunkard or a recent immigrant. Oh my goodness. Luckily, we don't have that category anymore, or some of the other weird ones. But we still do the same type of, we still create the same type of models in criminal justice. So here's one from the Pennsylvania Commission on Sentencing, where again, it's a point score and we add those points up, and that translates into a risk of being arrested. And why do we still use these kinds of models? It's because they're easy to use and easy to understand. Here is the 2006 Violence Risk Appraisal Guide. They rank you, I'm just zooming in here. They give you a score, and then that score translates into a low, medium, or high risk of violence. Okay, and then in medicine, there's so many of these scoring systems that they actually put them, they actually index them by subfield of medicine. So if you go to a website like Medscape, you can scroll down to your favorite medical specialty. Here I'm scrolling down to neurology, and then I clicked on seizure, and then I can click on the 2 helps to be score. And what it'll do is it gives me a calculator, and I punch information into the calculator, which is actually just a scoring system, and you get points, which translate into a risk of seizure in the next 6 hours. So the problem, of course, with these scoring systems is that when you design them by hand or with heuristics, they're not very accurate. So, of course, the question I'm going to be asking is how to design these scoring systems to have optimal predictive performance according to data, but also be understandable and easy to use by humans. And the thing about the 2 helps to be score that makes it different than all of these other medical calculators in all of Medscape is that it was not designed by humans or using heuristics. Now, I want to talk about this application for a while because it's really important. So let's say that you have an aneurysm in your brain that bursts. So you have a hemorrhage, and you have it's like a blood explosion in your brain. You have blood kind of all over your brain. And then you go to the hospital, they give you surgery, they put you in the intensive care unit, and they put EEG monitors all over your head. And those monitors are detecting for the possibility of a seizure. Now, these seizures occur in 20% of patients. They're very common, and they cause brain damage, and they cause death. They are very dangerous, and doctors will do really go out of their way to try to make sure these patients don't get seizures, because the seizures destroy their brain. So doctors will even give the patients medicine to shut off part of their brain, for instance, to prevent a seizure. And the only way to detect seizures is using EEG, because these patients, they don't shake. That's not that kind of seizure. It's a subclinical seizure. Okay, so we need EEG to predict seizures, and another problem with EEG is that it's very limited. There's a limited number of monitors, and there's a limited number of doctors to read those monitors, and they always don't get allocated well, because the monitors tend to stay on people way too long, and then people who need them don't get them, and so we need to figure out a better way to allocate these monitors, and in particular, we need to predict seizures in advance so that we know how to allocate the monitors. So I worked with neurologists to design the 2 helps to be score, which is the same score that we saw in Medscape. That was us who designed it. It's now widely used in hospitals, and it's small enough that I can fit it on a PowerPoint slide, but it's as powerful as our best black box machine learning models. And if you enter the information into the screenshot we saw earlier, it'll compute this score. Okay, so 2 helps to be is 2HELPS and then 2 points for the B, so that the doctors can memorize the whole model just by knowing its name. And it looks like a rule of thumb. I know it looks like a rule of thumb, but it actually was not created by doctors. It's actually a full-blown machine learning model. It was created by data fed into a machine learning algorithm. And it's just as accurate as our black box models. It doesn't force you to trust it. It's not like a black box where it forces you to trust it. interpretable models, they just have important practical advantages over black box models in that they don't force you to blindly trust them. So doctors can decide themselves whether they want to trust it. Also, doctors can calibrate the score with information not in the database, so that there might be unusual circumstances that might cause a doctor to adjust how they care for the patient. Like they might say, oh, this patient needs an extra point for this other rare condition that's not in the database. And also the score can be explained to non-physicians so that they can understand why someone's been taken off of EEG monitoring, for instance. Okay, now, as I mentioned, this model was created by a machine learning method on a data set. You can see it only has 6 factors in it, but those factors were chosen from a pile of over 70 different factors. And the points were also chosen, and then the scores were also chosen by the algorithm. So all that stuff was chosen by the algorithm. Now, as you can see, there's a combinatorial explosion in the number of models you could potentially choose from when you have a big data set like this. So I want to make a point that, designing an optimal scoring system, it might seem easy because the model looks simple, but it's not, right? There's a lot of different challenges you have to deal with when designing these scoring systems. So first of all, there's this combinatorial explosion in the number of possible model options. But also, you want the model to be as accurate as your black box. You want the model to be sparse, to have a small number of terms. You might want to add additional constraints, like fairness constraints or false positive rate constraints, something like that. You also would like it to have integer coefficients like 1, 2, and 3, and not 27 or something, right? The same thing as what people have been doing since 1928. Now, the typical approaches to designing these things are, well, you could, like I said, you could take a bunch of people and put them in a room and have them create a score. You could also have them fiddle around with logistic regression coefficients, which is a very popular way to do it. So what people often do is they select a subset of features, they run logistic regression, they scale all the coefficients, and they round them. And there's a lot of scoring systems that were designed using this kind of ad hoc process. I call it like fiddling with logistic regression. But the problem is that these methods don't work. They produce suboptimal scores, and they rely on humans to do high-dimensional constrained optimization, which no human can actually do. So here's an example of where that goes wrong. Okay, so this is an ElasticNet model for the seizure prediction problem for just a few variables, but it's difficult to use because if the patient has prior seizure and patterns superimposed with faster sharp activity, then how far is their score from 0? And what would need to happen to get their score to 1.6? Right? Can you memorize this model and use it on a patient as you're dealing with a million other things? Probably not, especially if it has more variables in it. Okay, let's try rounding the coefficients. That didn't work. I lost almost all the signal, and my probabilities are a mess. Okay, so back to ElasticNet. This time I'm going to scale all the coefficients by multiplying them by the best factor I can, and then rounding. Okay, so I multiply them by something and then round. This again is not very accurate, and it's really not what I'm looking for. It looks better, but it's just not as accurate as the 2 helps 2b score. Maybe if I fiddled with it some more, I could get something better, but it would be hard to get something as nice as the 2 helps 2b score. And fiddling is not what we should be doing in this case. We should be actually formulating and solving an optimization problem to get the answer rather than relying on the quality of my fiddling ability. So if computation was not an issue, what optimization problem would we solve? And I claim that we should solve this one. So this problem is the problem we use in RiskSlim, which is our algorithm that creates this. So RiskSlim also uses a cutting plane algorithm that I'm going to discuss shortly to solve this problem. But let me tell you what this is. So the first term is the logistic loss, which keeps the model accurate and risk calibrated. This term keeps the model nice and small so that it only has a few non-zero coefficients. And then this set of constraints says that we only want small integers as our coefficients, so numbers between -10 and 10. And as you saw, RiskSlim had numbers only 1, 1, 1, 1, and 2. That's because the algorithm chose those numbers. It could have chosen any number between -10 and 10. Now, if you are an optimization expert, you will know that this is a very hard optimization problem. It's a mixed integer nonlinear program. And this problem is difficult enough that if you threw it into a MinLP solver, it would take until the end of the universe to come up with an answer, even on reasonably sized data sets. But now, at least that I formulated it as a math problem, you can at least maybe kind of see why rounding doesn't really give you a good solution. So let's just think about here the logistic loss. We'll just take the logistic loss here and the integer constraints, and let's see what happens, okay? So if you actually, if you run logistic regression, you get the logistic regression solution, which is right in the middle here. And then these ovals are level sets of the logistic loss, okay? So logistic loss goes up as you go away from the logistic regression solution. Now, here, if you round, what happens? You get those solutions, but those solutions go against the performance grain. Like you actually lost a good chunk of accuracy when you did this, right? You lost a lot of performance when you did that. And you wouldn't have noticed that there is a solution at integer values right here that has very low logistic loss, right? So you should have actually gone out to here. Now, and the only way you could find this is by actually optimizing, right? You couldn't get it by rounding. And you might say, well, you know, you've drawn this picture in a way that you have these long, skinny level sets of the loss, and that's unrealistic. But it's not unrealistic. That's the thing. That's the reason for the whole field of mathematical programming. Most problems are like this. And if you have constraints, those make the problem even harder because the rounded solution can easily violate the constraints. Like you have constraints all through here. When you round, you're going to violate those constraints. And so now you can see why it's useful to actually solve the optimization problem. And the solution to it gives us models like the 2 helps 2b score. Okay, so I'll tell you in a minute how we solve the optimization problem, but after we solve it, let's go back to 2 helps 2b. So now when the patient comes in with their aneurysm, it bursts, they have their hemorrhage, go to surgery, go into the intensive care unit, get EEG monitors, they're being monitored here. The neurologist can look at the 2 helps 2b score and say, oh, it's 3 because the patient has this, this, and that. And so that person's high risk. So I've decided to place them on continuous EEG for at least 72 hours and start them on preventative medication for seizure. Now, so far, the 2 helps 2b score has been validated on an independent multi-center cohort. And what I'm showing you here is predicted versus true probability of seizure. So you want to be on the diagonal here. And the blue dots are from the study where we designed the 2 helps 2b score, and the green dots are from the validation on this independent cohort. I actually wasn't involved in the validation study at all. I'm not an author on the paper or anything. This was done by neurologists. Now, the 2 helps 2b score has been implemented at several different hospitals. And in the validation study, it resulted in a 63.6% reduction in the duration of EEG monitoring per patient, which, according to the doctors, has allowed them to monitor 2.82 times more patients than before. And so it's really allowed them to help reduce brain damage and save lives. That's what they tell us. Anyway, so I want to go back to talking about the machine learning algorithm that produced 2 helps 2b, which is called RiskSlim, and it solves this very difficult optimization problem. But before I tell you how this works, I need to tell you about cutting planes, because RiskSlim uses a cutting plane algorithm called the Lattice cutting plane algorithm. And I need to tell you why we're doing that, because we had to design our own cutting plane algorithm, and it's because traditional cutting planes don't work. So I need to explain traditional cutting planes before I explain what we did. Okay, so let's just explain traditional cutting planes. So let's say we have the logistic loss here. logistic loss is convex and non-negative. And I'm trying to minimize this function using cutting planes. Okay, so I have to start somewhere, which is here. I calculate the objective value and the gradient and create a cut. Then I'm supposed to minimize the blue surrogate here, which is going to be, it's going to be a piecewise linear function, but in this case it happens, I can't minimize it. I happen to know the function's non-negative, so I'm just going to go here. Okay, so then again, calculate the objective value and the gradient, create a cut, repeat. Okay, so now do it again. Okay, find the objective and the gradient, create a cut. And then eventually it'll realize that it found a solution because the minimum of the surrogate equals the minimum of the objective. So that's how cutting planes are supposed to work. But something goes wrong when creating models with integer coefficients. So let's show you where that happens. So let's say that you're here in the computation, and you can see that minimizing the surrogate involves solving a linear programming problem because these are all lines. But the solution, you see, might need to be here because the solution we want needs to be at an integer. Remember, the feasible region is the integer lattice. They have to be integers. So what that means is you need to minimize this function subject to the constraint that you get an integer solution. And this makes it a mixed integer program and not a linear program. And mixed integer programs are much harder to solve than linear programs. And you have to find the point on the lattice that minimizes this objective here, the blue thing. And you need to solve the MIP to optimality at every iteration, because if you don't, you have no idea whether you've actually solved the problem. And still at every iteration, you're adding a cut. And so as you add more and more cuts, the MIP that you have to solve gets bigger and bigger and bigger. And you have to solve it to optimality, and it grows more infeasible by the second. And that's bad. And no matter how big or small your data set is, after you add 200 cuts, the problem becomes difficult for the solver and it totally stalls. So here, after about 70 iterations, the solver took more than 10,000 seconds, and we just had to turn it off. We just couldn't do anything with that. So yeah, traditional cutting planes don't really work here. And then the optimality gap is supposed to go to 0, and it stayed at 100%, didn't even go down a little bit. So we designed a new cutting plane method that does not stall. And with this new algorithm, at each iteration, instead of solving the MIP from the surrogate, it solves the LP, the linear program, which is much easier to solve. But as you know, that solution is infeasible. Okay, so what do we do? What does it do with that? Well, if the solution to the LP happens to lie right on an integer point, you can create a cut. And then that's, it serendipitously solved the MIP. So that's one thing that could happen. But if it doesn't land at an integer point, well, you know that there are no feasible solutions in here, so we get rid of the whole area, okay? Because none of these are integers, so we just get rid of the whole thing, and we just tell the algorithm, you're never allowed to produce the solution that's in this range. And then we iterate separately in each of the two pieces. So here we solve the LP in each piece, and guess what? Serendipitously it landed on an integer point, so I can create a cut. And same thing over here. And it continues to proceed like that by either subdividing the space or adding a cut at every iteration. Okay, so now this actually really seems to solve the problem, because now even after 10,000 iterations, the solver completes in under 100 seconds, and the optimality gap gracefully goes down towards 0. So there's no stalling for the lattice cutting plane algorithm. It actually works, actually produces us a good scoring system. Okay, so, and it'll provably converge to the optimal solution, which is great. Let me just recap that in case you missed it. So here you're busy constructing this cutting plane approximation to your objective. And what you would do with the lattice cutting plane method is you solve the linear program. You're happy because it didn't take you that much computation to do it. But you landed at a non-integer coefficient, so you're actually unhappy about that. So what you do is you block off this whole region and you say, you're not allowed to give me a solution that's above 5 and below 6. Okay, so you split the problem into two pieces where you say, okay, in the first circumstance, it has to be below 5. In the second circumstance, it has to be above 6, and you solve both optimization problems. Okay, now if a subproblem leads to a feasible integer solution, you can add a cutting plane. Otherwise, you have to split it into two subproblems, and both of them, again, you solve with linear programs. And you just keep doing this over and over again so you get to the optimal solution. Okay, now LCPA is the only method that generates solutions within a reasonable time. The min-LP solvers don't work. Standard cutting planes, as you know, require solving larger and larger mixed integer programs, which is not something you want to do. Now, of course, when we had this algorithm, we weren't just going to use it for one problem, right? We used it actually for a number of different problems, and we also used its sister algorithm, SLIM, for a bunch of different things. Here are some examples. We used it for ADHD screening in adults. We used it for sleep apnea screening. We used it for the clock drawing test. The clock drawing test is actually really interesting. So this is where you're testing for cognitive impairment, like a cognitive decline. So for instance, Alzheimer's or dementia, Parkinson's. And the patient has to draw a clock with a digital pen, and then they have to copy that clock. And the pen is a digital pen, and keep track of all kinds of very subtle things that the user is doing, like how long they're taking to create their numbers or do their circles or whatever it is. And then it even keeps track of very subtle things they're doing, like little hooklets where it looks like they know where they're going off to the next number, so that it indicates foresight. And all of these very subtle signals go into a scoring system that a human can understand. We also used it for recidivism prediction. This paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications, so stay tuned for that. All right, now the question everyone keeps asking is whether interpretable models are really as accurate as black box models. And I talked about that earlier. And now the way we answer questions like this in machine learning is to compare algorithms by using benchmark data sets. So I'm going to grab a really great benchmark data set, which is the one from the Explainable Machine Learning Challenge. And in this challenge, they told us, create a black box and explain it. And we did not. Anyway, this data set is from FICO. It's a HELOC data set, so home equity line of credit. It's got about 10,000 loan applicants, and you have a bunch of factors of their credit history. It's a nice big data set, 10,000 loan applicants and a whole bunch of factors, right, credit risk. And the baselines that we want to make sure to hit are black box accuracy, which is 73%, and best black box area under the curve is 0.8. So you don't want to lose any performance over this. This is where you hope to get. But you want to get it with an interpretable model. Now, IBM, that got first place in the challenge, produced a very tiny little model, but they broke the golden rule of interpretable machine learning, which is that they lost performance. So they lost a little bit of accuracy, but they lost a tremendous amount of AUC. So AUC ranges from 0.5 to 1, and they went from what should have been 0.8 to 0.62. So that's not so good. Whereas the entry that we submitted, which won the FICO Recognition Prize, didn't lose any accuracy or any AUC as compared to the black boxes. And basically what it was 11 scoring systems. It was just 11 little itty bitty linear models that got combined together. Like 11 little kind of like logistic regression models that just got put together. And we made it look like a network because we didn't have any access to the domain experts, and it looked like they wanted a neural network. So we made it look like a neural network, but it wasn't. It was just 11 little scoring models. So we had these 10 subscales, each of which was logistic regression model. And then we combined those together into a final scoring system. So here I'm just showing you the delinquency score, which uses only 4 factors. And then this is the delinquency subscale where the person would get points for their percent of trades never delinquent. Like this person had a bunch of delinquent trades, so they got some points for that. The month since most recent delinquency was they had a delinquency within the last 8 months, so they get points for that and so on. And those points, they get added to a bias term and get sent through this activation function. And then based on this person's delinquency information only, they have a risk of 79.8%. So it's just a 4-factor additive model is what it is. It's just so tiny. And then we just combined all those factors, all of the results from all those 10 subscales into a final logistic regression model at the end. And that was it. That was all we did. So what we found was that even on challenging benchmark data sets, the interpretable model's accuracy is equal to the black box accuracy. So I want to go back to the topic of criminal recidivism and the COMPAS score. So as I said, this paper got into the center of a battle as to whether black box models are more accurate in criminal justice applications. Now, I want to point out that interpretable models are not equal to explanations of black box models. Explaining a black box is not the same thing as creating a model that's inherently interpretable. If you create a model to approximate a black box, first of all, that is an approximation, not an explanation, because the black box and the explanation could use totally different variables. So for instance, it's possible that the explanation depends on age, number of prior crimes, and the person's race, whereas the black box only depends on age and number of priors, because these 3 things are correlated with each other because of systemic racism in society. So you could say that nobody would make this mistake, right? You could say nobody would approximate a black box, see that the approximation depended on race, and then conclude that the black box depends on race, right? Who would be silly enough to make this mistake? But this actually might happen, and it actually did happen. And it happened with COMPAS. And it happened by the famous ProPublica group that wrote this famous article that everyone keeps talking about. So in this article, this is exactly the mistake they made. They approximated COMPAS by a linear model. The linear model depended on race, and then they declared that therefore COMPAS depends on race. So I just want to give you a little more details about what ProPublica did. So they showed that false positive rates and false negative rates of COMPAS varied by race. And we know that that would be true because the populations are different, right? The populations of blacks and whites in the database are very different. The blacks are younger and they have more priors, right? Because of that correlation due to, again, systemic racism. So ProPublica even knew this. And so they suggested this might not be a good comparison. So we should include age and number of priors and re-examine. So after including age and number of priors, they still found an approximation to COMPAS with a low p-value for the race covariate, which indicates that the approximation depends on race. And so they then concluded that COMPAS depends on race. But I think the problem is that I don't think COMPAS is linear in those variables. And so I think their conclusion just doesn't follow. So let me show you why ProPublica's assumption was particularly bad. So we take the data from Florida that was used in the ProPublica piece, this is the COMPAS data, and we plotted it. So this is, each dot is a person. This is age versus COMPAS score. And I hope you can see that people who are in their 20s are not going to get the same lowest COMPAS score than the people in their 60s. It's just not going to happen, right? There was a fairly sharp cutoff of COMPAS score for each age. And I think these are the minimum COMPAS score for each age. Maybe there were a few typos in the database, but overall, not pointing to a linear function of age, right? So you just can't do it. And it looks like COMPAS heavily depends on age here. So if they messed up the dependence on age, that could definitely mess up their analysis. So what we did was we were wondering whether if you take out this, like, so if we think that this is the contribution of age to COMPAS, we could just take that out and then find out whether the rest depends on race. So we asked, okay, does COMPAS minus this curve, F age, depend on race? And we did machine learning with and without race, and it doesn't seem to depend on race. So we didn't get the same result as ProPublica when we took into account the nonlinear dependence on age. So ProPublica's conclusion is pretty shaky. And what we found, again, is that race doesn't boost performance. Race is not actually useful for predicting criminal recidivism, just like we found in our interpretable recidivism paper back in 2015. So anyway, it makes you kind of wonder, like, if race doesn't actually appear in COMPAS other than through its correlation with age and criminal history, then how did they find these pairs of people, right? Because these examples were like the key evidence on how COMPAS depends on race. Because the white person in each pair had a longer criminal history and a lower COMPAS score. The thing is, if you look at these two people, the Black person is much younger than the white person. I mean, so like Vernon Prater, he just doesn't get the age points, right? He doesn't get the age points because he's old. So even though he has a long criminal history, he's much older, so he doesn't get the age points. And I'm not saying that I agree with this, but if they could compare two people of the same age, then it would be much more convincing that COMPAS depended on race in addition to the strong dependence on age. So ProPublica's claim not really holding up with respect to race. COMPAS might not actually depend on race, but I think there was a much worse problem with COMPAS that ProPublica completely missed, which is that humans are not very good at inputting data reliably, which is what caused the issue with Glenn Rodriguez. We had 100, if you have 137 factors entered by hand for each survey, 1% error rate on a survey can lead to 75% chance of at least one typo on a survey. And this, of course, is a huge disadvantage to complicated or proprietary models. And it's exactly what happened with Glenn Rodriguez that I talked about at the very beginning of the talk. So we were looking at the Florida data to try to figure out how often these typos might happen. And we found some strange inconsistencies in the data where these are people with the lowest COMPAS score, and they had these extensive criminal histories, like attempted murder in the first degree, resist, obstruct officer with violence, battery on a law enforcement officer. And this is COMPAS score was 1 out of 10 here. And we can't explain this other than through, some data issues that are not able to be explained. Anyway, these are people with COMPAS scores of 2 and 3. Again, very long, extensive criminal histories. We even think we found a typo in the COMPAS documentation because, we think maybe there's a nonlinear function of age, as I showed you. So anyway, we published this article attacking both ProPublica for explaining a black box wrong and COMPAS for being a black box where typos can cause decisions. And then we published it in the Harvard Data Science Review, and the editor of the Harvard Data Science Review, so the famous statistician Zhao Meng, he solicited 6 commentaries by famous statisticians and criminologists, and one of them was by the people who created COMPAS. And they wrote an absolutely scathing article saying that COMPAS is interpretable, which is pretty funny because if that were true, it would have saved me and ProPublica a lot of trouble. But in the mountain of criticism there, they admitted a couple of things that were super interesting. Here they wrote, the authors we have clearly taken an informal description of the violence score in the practitioner's guide. It wasn't informal, it was an equation. I don't know how much more formal you can get. Anyway, they said it wasn't intended to be a technical document, and discussions of appropriate variable transformations are beyond its scope. And we note that the skewed age variable is an ideal candidate for a normalizing transformation. And we were like, whoa, maybe we were right. Like a subtle admission of guilt there. And then for transparency, they said they were pursuing copyrights for the formulas for the COMPAS scores. And we were like, whoa, maybe we actually made a difference here. Anyway, so just to summarize, scoring systems are good when you optimize them. Typos are bad, and that happens more often with complicated or black box models, and evidence suggests we don't need such models in the justice system. All right, so I figured just to wrap up, I would just tell you very briefly about the problems that we're working on in my lab. You've heard all about scoring systems and their applications to healthcare and criminal justice. We've got a bunch of other stuff going on, including optimal decision trees with an application to material science. some work on interpretable neural networks for computer vision with an application to mammography, and some work on neural disentanglement. We also have a project on data visualization, dimension reduction, where you take high dimensional data, project it down, try to preserve its structure. And then I have I co-run the Almost Exact Matching Lab, Almost Matching Exactly Lab, for causal inference, where we are applying this to program evaluation in criminal justice. And then finally, a set of projects on understanding the set of good models and the importance of variables. Thank you very much.